Thank you for the introduction. And before starting, I want to acknowledge the work of my master's student, Chiara Dawood, and collaboration with Marco Broccardo, who was also a PhD student at Berkeley and who's now a postdoctoral fellow at ETH Zurich. I'll quickly go over the motivation and the fact that near-full ground motions have characteristics that are different from far-field ground motions, mostly known for the rupture directivity effect and the flick step. And these effects are not yet properly represented in modern codes and in current GMPEs. Our model mostly captures the rupture directivity effect. It can also incorporate the flick step. These rupture directivity effects depend on directivity parameters, which I'll introduce here. These are, they describe the geometry of the rupture relative to the site. So the directivity parameters that we use are the length S and the width D of the rupture between the hypocenter and the site, as well as the horizontal and vertical angles theta and phi between the hypocenter to site direction and the rupture plane. And S and theta are used for strike slip faults, while D and phi are used for dip slip faults. So this is just to introduce you to the terminology that we're using. So there have been ongoing efforts to understand, model, and simulate near-fall ground motions and their effects on the response of structures, including bridges and long-period structures. Did the mic stop?
The mic is,
yeah. I moved it so. Hello? Okay, it's working. These efforts include a procedure for simulation of near-fall ground motions that I developed under the supervision of Armen as part of my PhD. And the input required is the type of the fault, the magnitude, the distance to the fault rupture, the VS30 of the site, as well as the directivity parameters, S or D and theta or phi, depending on the type of faulting. The model accounts for the directivity effect. It produces a relative number of pulse-like and non-pulse-like ground motions consistent with recorded motions. And it's useful to generate synthetic ground motions for seismic assessment studies, for example. Our model has some limitations. The simulations tend to have a sharper peak of the response spectrum. They tend to overestimate spectral amplitudes at long periods, although this may be due to the fact that the GMPEs actually underestimate the spectral amplitudes at the longer period, or a mix of the two. The simulations also tend to overestimate correlations between spectral amplitudes at different periods. And this becomes important if you have higher mode effects. So these are the examples of the correlations between spectral periods. I don't know if the colors are clear, for recorded motions and for simulated motions. And you can see that our simulations tend to overestimate the correlations. So as part of the scope of the current project is to improve the formulation of our model, to try to fix these problems, to reduce the high correlations between the spectral periods, and also to explore an alternative method and more efficient method of fitting the modulating function. Another problem or thing to address in the current scope of the project is that the generated time series, due to the filtering that we're applying, was resulting in very long, almost zero paths before and after the simulated signal. Okay, and this is not practical for engineering applications. We're going to remove these yet another motivation for the current project is that the information that we have for seismic assessment studies is usually what is the fault that is contributing to the hazard, what's the type of faulting, its magnitude, its distance to our site, but usually don't have information about the location of the hypocenter and about the directivity parameters. So we're adding a layer into our simulations, which is to provide the users with proper distribution of these directivity parameters with knowledge of only the fault contributing to the hazard and its type and its magnitude and distance to the site. So this is part B of the scope, which is to reduce the size of the generated time series and generate ground motions for randomized hypocenter locations. Two other scopes of the project, which I'll quickly go over, are validation of the model by comparing nonlinear time history responses of bridges subjected to recorded and simulated motions, and possibly the incorporation of the simulations in GMSM procedures. And I'm targeting these parts of the scope in collaboration with a group at UC Irvine. So the outline of my presentation, I'll briefly review the existing model that we had, which is the simulations of near-fall ground motions for specified FM, ZTOR, RUP, VS30, and directivity parameters. Then I'll briefly go over the reduction of the time series size and the extension of the simulation procedure when we only know the specified site and fault, and this is done by randomizing, as I said, the rupture geometry and the hypocenter location. We can also do simulations to compare with the NGA-WES2 models, where again the rupture directivity parameters are not part of the GMPEs. And finally, I'll give some preliminary results from using an improved stochastic model. Our existing model is a site-space stochastic model in two orthogonal directions, and it accounts for both pulse-like and non-pulse-like motions. For the pulse-like ground motion model, it is in terms of 19 physically meaningful parameters that consist of both intensity parameters, such as RS intensity, pulse amplitude, duration parameters, and frequency content parameters. So they're able to capture the most important physical characteristics of a ground motion. Similarly, for non-pulse-like motions, we model them using using a model in terms of 14 physically meaningful parameters. And the simulation procedure, this is the input required. With this input, the first step is to determine whether the ground motion that is going to be simulated will be pulse-like or non-pulse-like. And this is done using the pulse probability model developed by Shahi and Baker. Then, if we want to simulate a pulse-like motion, then we use predictive relations for pulse-like parameters, empirical predictive relations that we've developed to generate the model parameters. We plug them into our model to get the synthetic time series. And I'm sorry, I guess the graphics here are not very clear. And we do the same if we have a non-pulse-like ground motion to simulate. Now, just a quick overview of the truncation and baseline correction that we're implementing now. The simulated motions are truncated before and after the strong motion signal, where the displacement amplitudes drop below 0.2 centimeters and below 1% of the peak ground displacement in both components of ground motion. So this is the originally simulated motion. The first step is to truncate it. The truncation results in non-zero displacements at the end of the motion, which is not realistic. So we apply a baseline correction. We fit a fifth-order polynomial, and we remove it from the signal to end up with the yellow signal, which is very similar to the original one. And this fixes the problem of truncation, bringing the displacement back to zero. So, and you can look at the effect of this truncation and baseline correction. It does not really affect the response spectra. Now, if we want to generate synthetic ground motions for a specified site with known VS30 and a specified fault with known type of faulting and magnitude, we're going to randomize the rupture geometry and the hypocenter location, because these are unknown to start with. Oh. Okay, so this is incompatible with the slides that I have. I guess I'll hopefully use these slides. So the first step is knowing the fault characteristics, so the magnitude of the rupture, the type of the rupture, and the geometry of the fault, okay, we want to generate our ruptures, rupture plane, coordinates, and hypocenter location. So first, to describe the rupture, we generate the depth to the top of rupture. And for now, we use this simple model by Campbell and al., which is magnitude dependent to determine the depth to the top of the rupture. Then the next step is knowing the type of faulting and the magnitude. Sorry, this is all messed up. We use the Wilson-Coppersmith relation to estimate the rupture dimensions. So we estimate the fault rupture length and width using these relations. So these are the mean and standard deviations. And we generate the rupture length and rupture width as correlated random variables. Okay. So once we have the rupture dimensions and the depth to the top of the rupture, we can then generate the rupture plane. And we sample it uniformly from the full fault surface. And these are examples of randomized ruptures. This is the input that we provide. And these are 3 examples of rupture realization. So the blue box is the fault geometry, and the red rectangles are 3 rupture realizations that are consistent with this input and consistent with the probability distributions that I presented earlier on. The next step is having the fault rupture to determine the location of the hypocenter. So for that, we use a model by Mayssa and al. To determine the hypocenter location along strike, and it is sampled from a truncated normal distribution, as well as the hypocenter distribution down dip, which is sampled from a Weibull or gamma distribution, depending on whether it's a strike slip fault or a dip slip fault. So these are some examples of randomized hypocenter locations for 3 scenarios. So in this case, I'm taking the same fault rupture plane, the same rupture plane, which is the red rectangle, and these green stars are 3 different locations of hypocenters that are consistent with the Mayssa and al. Model, and that are consistent with this input. Okay. So with that, we now have all of the information with the location, with the rupture dimension, rupture geometry, hypocenter location, and site location, we can actually calculate R, RUP, S, D, theta, and phi, which are the directivity parameters. So we can calculate these input parameters. Okay, and then we can go through our simulation procedure again, where F, M, and VS30 are provided, but Z-Tor, R, RUP, S or D, theta or phi were simulated given this input parameter, and we can go through the simulation procedure as explained earlier on. Okay, I'll take the slide. We can also generate near-full ground motions for comparison with the NGA WAS2 models, which do not include directivity parameters as their input. So again here, we're going to randomize the rupture geometry and the hypocenter location, but we're also going to randomize the site location by sampling sites uniformly at a distance R up from the fault rupture surface. And these are the so-called racetracks. So here we have 3 different realizations of with variable rupture length, hypocenter locations, as well as site locations. So this can be repeated many times in a Monte Carlo simulation framework to get the corresponding distribution of the directivity parameters for the desired input. And then from the geometry we can calculate S or D and theta or phi. This is an example showing 600 of our simulations for this input scenario, and the comparison with the NGA WAS2 GMPEs. So here I'm showing in colors the 5 different GMPEs. The dashed line is the median spectrum of our pulse-like motions. The solid line is that of our non-pulse-like motions. So you can see that the pulse-like motions have larger amplitudes at the longer periods. The percentage of pulse-like motions is 20% out of the total simulations, which is consistent with the observed ratio and recorded motions. And if we compare the global median of our simulations, of our 600 simulations with the NGA West GMPs, we see that it falls within the range of that is spanned by the 5 NGA West GMPs. Okay, so this is a validation that we're capturing the recorded ground motion levels. Also, at most periods, our simulated motions fall within the median plus minus 1 sigma levels predicted by the NGA West 2 models. Finally, the last part is the improved stochastic model, which consists of a modulated and filtered white noise process defined via a spectral representation. So what we're proposing is to replace the moderated filtered white noise model that we've been using with an improved version. The improved version includes a non-parametric modulating function. It has a larger number of parameters, but it's simpler to fit. The filter is defined in the frequency domain, which makes the fitting of the filter parameters more directly on the evolutionary power spectral density, instead of having making use of proxies such that the cumulative count of zero level up crossings or the cumulative count of positive minima and negative maxima. We're still exploring several alternative filter functions to see which one gives us the best performance with the minimum number of parameters. And the application of the high-pass filter becomes a lot easier because it's directly applied on the EPSD. Here I'll just illustrate the modulating function. So this is a recorded motion, and this is its cumulative RS intensity variation over time. And when we are using a parametric function, this is the type of fitting that we are obtaining. So we were kind of capturing the overall variation, the maximum, the level at the end, and this is the fitted modulating function. Now in this case we have two peaks in the amplitude of the recorded motion. So now with the non-parametric modulating function, what we're doing is we're capturing the times at different points of percent of RS intensity and simply fitting a spline between these points. So we're making use of a larger number of points, but we're able to capture these two peaks in the amplitudes. And the fitting of the modulating function in this case is actually a lot easier, a lot faster to obtain. These are some preliminary results comparing the response spectra of recorded motions and simulated motions using fitted model parameters. And we are able to get a good match of the mean and median spectra. Here the 6 subplots are exploring 6 different versions of the filter function. So this is still work in progress. But all of these alternatives are actually fitting the response spectra levels quite well. And what we're interested in was also the correlations. And again here, even with a simple filter function, we're able to capture the correlations between spectral periods better than what we were in the original model. To end with the work in progress and future work, for the synthetic near foreground motions being simulated for specific site and fault, what we're working on right now is also randomizing the Z-TOR. We've been using a deterministic function for now, and we want to generate it and simulate it jointly with the Rupture Dimensions. We also want to randomize the site location for non-vertical faults, which is a slightly more difficult geometric problem. And finally, for the improved stochastic model, we're finalizing the model formulation. We need to confirm that the improvement that we've seen extends to pulse-like near foreground motions. We haven't included the pulse in the results I've shown so far. And we still need to develop predictive relations and possibly combine near fault and far field simulations in a single framework. Thank you, and sorry about the problems with the.
Any questions for Mayssa?
This is awesome. I have a couple of questions.
Yes.
One is, you're comparing with the GMPEs,
Yeah.
so you're turning off, doesn't one of them at least have a directionality with the directivity parameter?
No, so these are the. So here I did not include the directivity models, which, like, there are 5 different directivity models that were also developed, part of the peer funding, but there was no consensus, and this is still work in progress as to how to incorporate them into the GMPEs. So these are just the 2014 GMPEs with no directivity parameters as input, at least to my knowledge.
Have you compared this to data? Do you have, I don't know if I may have missed it, just comparison to actual measured recorded ground motions?
So the fitting itself is done on the recorded ground motions.
Oh, you've got
And then
ground
what,
motion itself.
I haven't shown it here, but we've done checks in terms of simulating ground motions using fitted model parameters and comparing them with their recorded counterparts. But I don't have the figures here. So as part of the fitting procedure and validation procedure, we've compared simulations using fitted parameters to the recorded motions that were used to fit those parameters.
And one last question.
Yes.
Is, are you looking at directionality at all? Because I've seen you're doing everything in the fault normal, fault parallel.
So no, we're not doing it in the fault normal for parallel. So let me go back to the ground motion model. I quickly skipped through this. So for the pulse-like model, we formulated in the direction of the largest pulse and the corresponding orthogonal direction. And as part of my PhD, I looked at a model to predict the direction of the largest pulse relative to the strike of the fault. So it tends to be mostly the in the fault normal or strike normal direction, but there is variability in the actual direction of the largest pulse relative to the strike of the fault. So this is taken into consideration in the simulations. For the non-pulse-like motions, the model is formulated in the major intermediate directions, and there's a tendency here for this to be randomly oriented relative to the strike of the fault. So there is not much directionality in the major and intermediate principal directions.
So you're doing a 2D kind of.
Yes, and so the directionality is taken into consideration.
Any other questions? I have a question. So you use iris intensity. Did you try something like CAV?
I did at some point when I was still a student. I looked at the like replacing iris intensity with CAV with CAV, and the results were more or less similar. I think one can capture like the intermediate periods better than the other, but overall there wasn't much difference. But it can be further investigated actually. So it may depend on the application also.
Just when you square it, the big number become bigger and the small number become very small. Take the absolute velocity. Okay, any other comments, questions? Okay, thanks, Mayssa.
Thank you.